So I'll hold up the picture. This is lecture 8 of operations research. If you haven't, I took some beautiful photographs this weekend. This is actually, I'll zoom in a little bit. This is a picture of an apple orchard in Lanesboro. I guess I should be holding it this way. This is trying to play with the color. Anybody know why this picture bothers me so much? All the apples on the ground. In terms of opportunities all around you for increases in efficiency, there's got to be something they can do about all these apples on the ground. Rows and rows and rows of apples on the ground. Do you want to hire workers to be just walking back and forth, and just constantly picking up the apples so that they're not on the ground too long and getting moldy? What do you want to do? Is it worth doing this? How many of you have taken an economics class? Did you ever do the problem about guarding art in a museum? You know, how many security guards should you have to make sure the artwork isn't stolen? At some point, the additional cost of the security guards is greater than the value of thefts that they save. And for some things, then it's, well, is it worth hiring the additional guards? Now, there's of course other things than just the monetary value. But for something like this, how much would it cost to hire people to do something with all these apples on the ground? So just things to be thinking about as you're going through life. Just whenever you see opportunities, what can you do with it? All right, so today we're finally going to prove a real theorem in operations research. It's going to be related to linear programming. So right now we've done the canonical linear programming problem. Given any problem, we can convert it to a specific form. So anybody want to tell me what the canonical form is? So what's our canonical form? Somebody should remember to be willing to speak up. So what's the canonical form of a linear programming problem? Everything looks like the following. So you have equals instead of equality. So you have AX equals B. What do we know about the x's? The xi's are non-negative. It's a lot more convenient to have greater than or equal to 0 because now we have a closed set rather than an open set. And then there's one other thing. What's the objective function? Yes? So we want to minimize C transpose X. And we looked at the diet problem, and for the diet problem, we saw that we had some kind of polygonal or generalized polyhedral boundary, and we saw that if we were at an interior point, we could flow to a boundary, and the cost would be the same. And then we could move on the boundary to a vertex. So we only have to check the vertices. This is not a complete proof of the whole general case, but the general principle is the same. It's enough to check the vertices. Now the problem is the number of vertices as your number of variables grows and your number of constraints grows becomes far too numerous for direct brute force exhaustion. In principle, linear programming is trivial. There's only finitely many places to check them. Practically, however, that's useless. So we need an efficient way to search through the space. Anybody know which Big Ten school I root for? I'm sorry? I'd like the full name, please. The Ohio State University. Okay? We are not looking for the optimal solution. We are looking for a optimal solution. Or I guess if you're an English major, an optimal solution. Okay? What is the difference between looking for the versus a? When there's a, there's possibly more than one. And as long as they give you the same value for the objective function, it doesn't matter which one you choose. So we have some freedom. So we are not going to be looking at all possible optimal solutions. We're going to find a method to zero in on one that is easy to find. Now, if we put in additional constraints, if we put in additional objective functions, then we would probably want to go back and revisit some of these other candidates that we threw away. But in a situation like this, we don't have to check all the optimal solutions. We just have to find one of them. And that's going to be a huge advantage. So the first thing we're going to do today is we're going to look at another form of a linear programming problem. It's going to be related to this. And the idea is if we can solve that, we can get information about this. And ideally, we'd like to be able to use it to completely solve this. We won't be able to always do that, but we will at least be able to use it to get some sense of how close we are. I think I've given this example before. Imagine you own, I'll change it to United Airlines, because we have a student who's not here today because of United's incompetence. Okay? So imagine you own United Airlines. What is your objective? Maximize profit. How do you do that? Probably fly the right passengers at the right time. They're working on that part. Okay, they at least understand what they're trying to maximize. Right? So you're United. You want to try to maximize. Let's say you know that you're going to have $400 million in profit if you choose the optimal schedule. And let's say it takes 3 years to figure out what that optimal schedule is. Is it worth flying no planes and waiting 3 years to find that optimal schedule? No, of course not. What if you can get within $100,000 in 5 hours work? Is it worth waiting? Yeah. 5 hours work is not that bad. So the question is, how much time do we have to spend to get to a certain percentage of the optimal solution? This is a little bit mysterious at first, that before we even do any calculations, we actually can get bounds on how far away we are from the optimal solution. So we can see, is it worth spending additional time trying to refine things? Especially since when you look at these constraint matrices in general, we may be guessing at what a lot of these parameters are. If these are coming from real-world problems, we may not know what is the demand of people from flying from Albany to Orlando. And so we have to put some guesses in our model. So insisting that we have the correct solution to a problem where we have imprecise information, that doesn't seem reasonable. So the whole point of what we're going to do is we're going to get a way to codify how close we are and then see how much more work we need to do. So the main idea is this notion of duality. How many of you have seen duality or studying a dual problem in another math course? Which course? Linear algebra. So where did you do a dual problem in linear algebra? Okay. Anybody else remember? So if it's been done before, it's not been really hammered home. Okay. The idea is we want to switch to an easier problem or a related problem to study and use that information to get back. Yes?
Was something about allocating hours to a machine versus a person.
Okay.
And you have to figure out what's the optimal way to share or to allocate work hours to get the problem done most efficiently.
Okay, so you've got a bunch of people coming in with problems, and you have a bunch of different computers and machines, and you're trying to decide how much each one should do on each thing?
You have a person and you have a computer, and each person, both of them work at different speeds.
Okay.
And you want to figure out how much of the problem you want to allocate to the person versus the computer.
Okay, I'm not sure if that's a duality problem.
I remember they called it a dual problem. I'll look at my textbook.
Okay, look at the textbook. I'd like to see more about that. You definitely have two different things going on, so they might be using dual in that sense. So here, duality is something that's related. So one of my favorite examples is the chess problem. And I think I'm giving you some homework problems related to this. So you have a 5x5 board, tax cuts, budget issues. We can't afford the full 8x8 board anymore. Okay? Can't even afford windows in a classroom. Right? And that will sadly hold for the new Bronfman as well. All right, so we have a 5x5 board. Does everybody know how queens move in chess? Queens can move diagonally, horizontally, and vertically. So you want to place 5 queens so that 3 pawns are safe. So what that means is there have to be 3 squares on the board that are not being attacked. So 1, 2, 3, 4, 1, 2, 3, 4. Where should you put the first queen maybe to minimize the number of squares attacked? Corner. It seems reasonable because if I put a corner here, I've got 4, 4, 4, and then one more space which is inaccessible. If I put it in the center, I'm definitely taking over a lot of spaces. So it's an interesting question. I'll let you do this as an exercise. Where should you put the first queen to minimize the number of squares attacked? What am I trying to do here?
Maximize free spaces.
Right, but what am I doing by putting my queen in this row? Okay, I think you do.
Limiting the attacking.
Limiting the attacking. I'm doing what's locally best. So one way of solving this problem is maybe let me do a sequence of things that are locally best. This is probably not going to work. So I don't actually know what the sequence is of what's locally best. Let's just choose something like this, just for definite sake. And then these queens, would kill those squares. These ones would kill all these squares. These would kill those squares. We kill these diagonals. We kill these. And we kill these. And then this one kills these two over here. This one kills that one. Okay. This is a very bad choice, right? By doing it like this, I think if I've done the calculation correctly, not one square is free. So we can't put down any pawns. So the question is, how should we put down the queens in such a way that we can put down 5 pawns safely? So let's just do this by brute force. How many ways are there to put down 5 queens on a chessboard? Yes. 25, choose 5. And I've written down the numbers over here. So there's 25, choose 5. And that's going to be 53,130. All right, that's not that bad of a number. A computer could easily go through 53,000 alternatives, and for each one of them, check and see how many pawns can be safely placed. The problem is, of course, if we now go up to a 6 by 6, 7 by 7, 8 by 8, how quickly is this growing? And this would in general be n squared choose n. So the general case would be, I think, n squared choose n. And then the estimate is how fast is that going? Okay? So that's a nice question. What is growth rate? So for small values, it's not so bad. Did we do tic-tac-toe in this class? Or was that probability? Okay, that was probability. So there will be a talk on interesting, fun versions of tic-tac-toe. They do exist on Wednesday. So let's quickly look at tic-tac-toe. Okay? Goal is to get 3 in a row. Everybody has played tic-tac-toe. I am the reigning champion at the Williamstown Elementary School. I have a huge number of victories, 1 tie, and no losses. Okay? How many opening moves are there in tic-tac-toe? How many opening squares can you move in tic-tac-toe? 3. If you were a little kid? 9. And so when I was teaching this to my daughter's kindergarten class many years ago, they had trouble counting to 9. And we were, oh God, we're in trouble. At this level, it's not that hard to see there's 9 squares, there's 9 openings. But then if you think about symmetry, all those corners are the same under rotation, flipping, stuff like that. All the middles are the same. And so there's really only 3 opening moves. And what you can then do is for those opening moves, you can look at the responses. So for instance, if somebody starts off with a corner, first of all, it's not a great opening move, but let's say they start off with a corner, how many responses are there?
4.
So let's see. 1, 2, 3, 4, 5. There's 5 responses. So if you just use some symmetry like this, you go to, I think there's 12 pairs for the first 2 moves. There's 5 coming from moving here, I think there's 5 coming from here, and then there's 2 coming from the center. If you just did it naively like this, there would be 9 times 8 equals 72 for first 2 moves. And so you go from having 72 cases to analyze to just 12 cases to analyze. This is why I can kill them on the elementary school playground. I don't have to go through the whole set of alternatives. From a coding perspective, which is easier to code, the one with symmetry or the one without symmetry? Which computer program would you rather write? One with symmetry. Why? Okay, so why wouldn't you have to write as much code? Well, no, I agree that there's significantly less things to check. What I'm not necessarily agreeing with that you have to convince me is why is it less code to write? You could be a much better programmer than I am.
Would we have to write extra code to detect symmetry?
So that's my question is, how would you have the computer examine the different symmetry cases? Would you have to be writing code for this? I can call these squares 1, 2, 3, 4, 5, 6, 7, 8, 9, look at all 9 factorial permutations of the numbers 1 through 9, and each one of those give me a game, and just go through the game and see what happens. So I think from a coding perspective, it's much easier to do the brute force approach. From a computational perspective, however, I would much rather do something like this and have some symmetry gains. So I would say that there's a little bit more work in the code here, but for a very complex problem, it's a great trade-off. And this is the perspective you really have to adopt when you're doing these problems. You first do a very quick calculation. Is this problem sufficiently involved that it's worth being clever? And if the problem is straightforward enough that you don't need to be clever, then don't be clever. Write the short, simple code. Did I give you the numbers 1 through 9 and the sum equaling 1? Was that also, that was here? Okay, and that was a great example of it wasn't worthwhile trying to write good code. Just write really bad code because I only have to run it once. This is something that you only have to run once. But I agree that this is a much better way to go. So this is using the idea of symmetry. And the idea of symmetry goes from 72 to 12. That's a huge savings. That's a factor of 6 savings. All right, if we go back to the chess problem, we looked at how many ways were there to place the queens. We said there's 25, choose 5. How many ways are there to place that first queen? So if we go back to chess, how many ways are there to place that first queen? Up to symmetry. So how many ways can we place the first queen up to symmetry? Yes? 9? Why 9? Okay, so one is to take the first box. 1, 2, 3, 4. 1, 2, 3, 4. And what you're saying is, look at the first box here. So that's definitely a savings. And that will give you 9 moves. But I think you can actually do better than 9 if you look at the first box. Some of the things in the box are the same. So what can you refine that to? Yeah. If someone can do 5, I would be amazed. I get 6. I think I have to do 1, 2, 3, 4, 5, 6. That's the best I can do. And now we go from 25, choose 5 to 6 times what? So once we place the first queen, how many places are there to choose the remaining 4 queens? What would it be? 24, choose 4. And that would be 10,626, I think. Well,
what if you put, say, one of the queens, like what if you say you choose 1,
right.
and then the second choice happens to be square 6?
Oh, no.
So this definitely overcounts.
This definitely overcounts. Just like,
Okay.
well, this overcounts a little, yes.
Not by, like a huge factor.
Well,
Maybe like a factor.
but when we did 25, choose 5, does that overcount? So there we're choosing spaces. And so here there is a little bit of a difference because now we have a special order for one piece. So what you could even do is you could say, let's assume we have a certain number of pieces maybe in here, but it's starting to get more complicated. The goal is to write short, simple code. We only have to run this once. And so this overcounts a little bit, but even with the overcounting, it's a factor essentially of 5 savings. And you could ask, how much of a savings is it as you get larger and larger and larger? And it could be a huge percentage savings, but the problem could be so computationally large, it's just not worth doing. Okay? So the goal is to get even better. So the solution is to solve the dual problem. So right now, what are we doing? We're putting down queens so that 5 queens so that 3 pawns are safe. There's another way to view this problem. How else could we view this problem? So right now, we're trying to put down 5 queens so that 3 pawns are safe. Yes? I'm sorry?
Instead of just trying to place queens, you could place a pawn.
Yeah, you could place pawns. I want to put down 3 pawns such that there are 5 squares that don't attack them. Or if you want, I would want to put down 3 queens so that 5 pawns are safe, and then convert queens to pawns and pawns to queens. Either way is fine. So instead of putting down queens, I put down pawns and flip, or instead of trying to put down 5 queens, I put down 3 queens. Either perspective is fine. So let's place 3 pawns so that 5 squares do not attack any. Okay? How many ways are there to do this naively?
What about you?
25, choose 3. Which, what a surprise, I have written down over here is 2,300. Much better. Almost another factor 5 savings. What could we do to improve this even further? Symmetry. So how many places are there for the first pawn? There's 6 for the first pawn, and then 25 choose 2, which is 1656. 24 choose 2. Thank you. Which is 1656. So we've gone from something in the 50,000s of cases to a little bit under 2,000. It's less than at least the current year. All right. This is still too much to do by brute force. Right? Well, I guess if your life depended on it, 1,600 cases is not horrible, yes.
Why is it still 2, or why is it 6?
Because there's 6 places to put down the first pawn. Up to symmetry.
You didn't want 5 squares that don't attack.
Well, I'm placing down 3 pawns. And then once the pawns are placed, I then ask which squares attack them. And I shade off all the squares. So for instance, let's say I place my pawns here, here, and here. And I want to see which squares would attack these pawns. So anything in this row would attack. Anything in this row would attack. Anything in this row would attack that pawn. Anything in this column would attack. This diagonal, this diagonal, this diagonal. This one does not attack anything. So I could put a queen here, and I could put a queen here. So this is at least a proof that you can put down 2 queens with 3 pawns safely. And the question is, what's the maximum number of queens you can put down such that 3 pawns are safe? And there's lots of different generalizations you could have on the board. As you keep increasing the size of the board, if I put down n queens on an n by n board, how do you think the number of pawns that can be safely placed should grow? This is a good time to, I guess, mention the following phrase. Anybody ever hear of OEIS? The Online Encyclopedia of Integer Sequences. This is actually, it is a useful sequence. Useful site. I will be mentioning it a little bit later, probably Wednesday when we talk about Euclid's proof of the infinitude of primes. If you have a sequence of integers, you can feed it into the OEIS, and it will tell you all the places it knows where the sequence appears. And it will tell you whatever properties people have inputted about it. It'll tell you recurrence relations. It'll tell you closed form expressions if they exist. It'll tell you situations where they arise. It'll tell you growth rates. It'll give you references. It is a phenomenal site. I actually once gave a talk when I was a postdoc on how to prove theorems by using the OEIS. if you are proving things by induction, which is one of our favorite ways of proving things, what makes inductive proofs a lot easier? If you want to prove something by induction, what do you want to know?
The base case exists.
A little bit more than the base case.
You want to know the general rules.
You want to know the general rule, right? If I tell you, prove a formula for the sum of the fifth powers of integers, is this a hard problem for you? Hopefully by the time you get into 377, no. You've hopefully seen induction before, and if you know the formula, you do the base case, you assume it holds for n, and because you have the formula, then you just show it holds for n plus 1. If you don't know the general formula, however, it's much harder. You have to find some way to sniff it out. The OEIS is a great way to get a sense of what the initial formula should be. There was a problem, this is a generalization of one of our homework problems where we had this method where we were trying to estimate the sum of 1 plus 2 plus 3 plus ... plus n. And we were breaking it in half, and then we kept incorporating the estimate and kept correcting it and improving it. And with some of the students, I got a sequence of exponents as follows. 2, 3, 5, 8. What would you guess the next number is? 13. The next number was 12. And so one of the things I quickly noticed, because I've done this for so many years, is this is a 1, this is a 2, this is a 3, this is a 4. What would you guess the next number is? 17. And the next number was 17. So we haven't proved that the pattern continues, but we were at least able to sniff out the pattern and guess what comes next. The more terms you generate, the fewer terms in the OEIS will typically match it. And eventually you will get down to, here is essentially the only candidate that's known. And it's a great thing to try. So I strongly recommend when you have sequences of integers, trying the OEIS and just getting a sense. So here what we've done is we've looked at a dual problem. Is rather than attacking the original chess problem of placing 5 queens, we're looking at the equivalent problem of placing 3 queens. And then we convert queens to pawns and pawns to queens, or we put down 3 pawns and try to have 5 squares the same. Frequently, the dual of the dual is the original problem back. But the idea is it's a problem related to the original, and sometimes just the way the computations are arranged, it's easier. Okay? Any questions about the chess problem? Okay. How many of you have seen the Fourier transform? Okay. So the Fourier transform, f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. Given some function f, you have a new function f hat. There are at least 3 different normalizations to use for the Fourier transform. One of the advantages of being the professor is I get to choose, and this is the right one. Some people, I mean, you can argue as to whether or not there's a minus sign, but most people agree that there should be a minus sign here. Some people will not have the 2 pi here. They're wrong. Some people will have a 1 over 2 pi outside. They're also wrong. And then there are the wusses, there are people who try to appease everyone, and they try to have like a 1 over square root of 2 pi outside to go halfway between having the 2 pi and not having the 2 pi outside, and they're probably the most wrong of everyone. The reason this is the right way is because of a formula I love to use, Poisson summation. And what this says, and I think I've given you a homework problem on this, is the sum of n through the integers of f of n is equal to the sum of n in the integers of f hat of n, if my function f is nice. Sums like this arise very frequently in probability in number theory. And frequently what happens is you have a slowly decaying sum here, and when you take the Fourier transform, you get a rapidly decaying sum. So frequently just one term, the n equals 0 term, is enough to do a phenomenal job of estimating what's going on. And this is the power of something like the Fourier transform. It's converting it to a related sum that's easier to analyze. If your function f is even, f even, then f hat is f again. So if you take the Fourier transform twice, you return to where you start. If your function is not even, you have to do it 4 times. One of my thesis advisors, Henrik Evanits, is a master at this. And in one of his papers, he applies Poisson summation and then applies Poisson summation again in a non-trivial way. Now, if you apply Poisson summation twice, you return to where you start. So what he did first is he applied Poisson summation, did some analysis, and then he applied Poisson summation again to what was left in a very non-trivial way. But the idea here, the theme here, is that you want to convert from hard problems to easier problems. And it all comes down to what is the difficult algebra going to be. All right, so this seems to be, this is the eraser that works. Okay, so what I want to do now is I want to look at the dual problem for linear programming. So one of the nice things about being at the blackboard is I can leave the canonical form of the problem right here and write the dual problem right here. So now I will have, I think I want to use less than equal to, yes. So the constraints is y transpose A is less than equal to C transpose, and yi is real, and the objective is to maximize y transpose B. And remember, y transpose B is just the dot product. As a nice exercise, the dual of the dual is the original. So the first thing is, do these problems look related to each other? Do we agree that they look related? They have the same cast of characters. They have the same matrix A. They have the same vectors C and B. The difference is now we have our new variables y that are real, and now we have y's on the other side, and this is why we have transposes. Okay? So it's not initially clear that the dual problem is worth studying. But it's at least related to what we're looking at, so there's at least a chance that this is a good thing to do. So one of the reasons the dual problem is so nice is it gives us a way to find a condition on whether or not we have an optimal solution. So let's see. How many of you are CS majors or have gone deep in CS? Okay, excellent. It's so nice to have this many hands going up in the class. So you've done the P versus NP stuff. So there's all these different algorithms, and the goal is to figure out how long does it take for them to run. There's a lot of algorithms that are very tough to do. It's very tough to solve the problem, but it's very easy to check and see if a solution is correct. So what do we call those classes of problems? NP complete. Okay, so for instance, here is what is currently believed to be a hard problem. I have to say currently believed because I can only talk about what is known publicly. I have no knowledge that I'm willing to share about what the NSA and other organizations like that know. Factorization is thought to be hard. Why is factorization hard? Smart people have looked at this for a long time and have not published a solution. Okay, so if I give you a number, it's hard to tell if the number is, it's hard to tell how the number factors. We actually know a fast way to tell if a number is prime. This was proved in 2002. And if people want, when the camera is not rolling, I will tell some stories about the paper, P equals NP, I'm sorry, primes in P, where they found a proof, a constructive way to determine if a number is prime. Unfortunately, if the number is composite, it doesn't give you a factorization. It just tells you the number is composite. So it answers the question, is your number prime, but not in a useful way if you want to break it down. So if we assume factorization is hard, it is difficult to write n as pq and find p and q. However, if somebody gives you a number, easy to check if r is a factor of n. So how would we check to see if r is a factor of n? Yeah, just divide. Division is not that bad. So it's very easy to check and see if a number works. So if somebody has a claimed solution, you can quickly check and see, are they right? So one of the things we want is we want good conditions that are useful in practice. So when we're looking at our linear programming problems, the goal is to find the optimal solution, or failing that, at least get close to the optimal solution in a reasonable amount of time. So the first thing we're going to do is we're going to look at the dual problem, and we're going to see how the dual problem gives us a really simple condition to check and see if we have an optimal solution. Then the question becomes, is this condition practical? It tells me to do something. And if I can do this, and I get the following result, we have an optimal solution. Great! Well, can I actually do the thing that I need to do? There's a lot of situations in mathematics where we know a solution exists, but we may not know a good way to find it. Okay. So here is the first big theorem. Let x be a feasible solution to the canonical problem and y to the dual. If, I think it's y transpose b if y transpose b equals, I think, C transpose x, then x is optimal. And we always have y transpose b less than or equal to C transpose x. Okay? So we have a linear programming problem, and we have its dual. X is a feasible solution to the original problem. So x satisfies the constraints, and its coordinates are non-negative. Y is a feasible problem to the dual. It satisfies the constraints, and its entries are real. If it turns out that y transpose b happens to equal C transpose x, then x is an optimal solution. However, we always have y transpose b is less than or equal to C transpose x. Okay? So this is a condition that will tell us if x is optimal. If we can find a solution to the dual problem, if we can find a feasible solution such that these two expressions are the same, we win. We will always have y transpose b is less than or equal to C transpose x. Now let's think. Let's say you find a solution to the feasible problem. I'm sorry, you find a solution to the dual problem. That gives you an estimate for your minimum cost. So let's aside. Say y is feasible for a dual. Then minimum cost for canonical is what? What kind of bound do we have for the minimum cost for the canonical problem? It's a low bound. Is at least y transpose times C, or times B. And the reason is, according to this theorem, for any feasible solutions x and y, C transpose x, our cost, is greater than or equal to y transpose b. So if we find even one feasible solution for the dual problem, we have a lower bound on the objective function. So let's imagine these two are not equal. Let's imagine this is $400 million and this is $402 million. We know we're not off by that much. So this is a great way to get a bound on how far you are from the optimal solution. Very, very easily. All you need is some feasible solution. So maybe we can find a really crappy, I'd use stronger language, but this is being recorded. We could find maybe a really crappy solution to the dual problem. And that will give us a really crappy bound for the optimal solution for the original problem. Then maybe we do a little bit more work on the dual problem, and we get a better solution. We plug this in, we get a higher value here, we get a better bound. And then the more work we do on the dual side, the better estimate we get, the better lower bound we get on the smallest cost to the original problem, the problem we care about. And if we're eventually lucky enough to have an equality, then we know we found an optimal solution. So of course this begs the question, so instead of trying to find a solution to the canonical problem, now we're going to try to find a solution to the dual problem. How easy is that? We leave that as an exercise for Wednesday. All right, your future self can deal with that. Right now, we're going to just deal with this. All right, so let's proof. So the proof is just algebraic manipulations. And the question becomes, what do we want to study? What's a natural thing to look at? All right, we have Y transpose B. So if you look on the board, something should be screaming at you. Think of me when you think of B. AX. So let's look at Y transpose A X. And this is the same as Y transpose AX. So one way is if I group these two like this, AX is just B. And if I group it like this, I now have something coming on from the dual problem. So it all comes down to, I'm looking at this quantity Y transpose B. Where does B come from? B comes from A applied to X. So this expression here is just Y transpose X. But what do we know about Y transpose A? Y transpose B, sorry, Y transpose B. Thank you. What do we know about Y transpose A? It's less than equal to C. And so when you do the algebra, you'll get less than equal to C transpose X. Just from substituting in. And so we've just shown that no matter what values we take, if Y is feasible and X is feasible, this relation must be true. Yes?
Could you explain once more why we have equality in the canonical form? Is it because we're only going to be checking the boundaries?
No, it's because we have shown that we can always convert any linear programming problem to canonical form. And so that if we have an inequality in the original formulation, we add additional slack variables. If we had a less than instead of a greater than, we can multiply the row by -1. You can now see the benefit of putting something, at least theoretically, into canonical form. I only have to do an argument of this nature. I can assume now the elements of X are non-negative, so I can now say that this dot product, I'll keep the inequality. I know that Y transpose A is less than equal to C transpose. If I replace this with this, I increase my quantity. Just looking at what's going on component by component. If some of the X's were negative, then if one of these components is increased when I replace Y transpose A with C transpose, if this was negative, that could result in decreasing this right-hand side. So it is absolutely essential that X is greater than or equal to 0. So we need Xi to be greater than or equal to 0. So the whole point is it was worthwhile to spend the time we did on canonical form. It makes the argument here much easier. This allows us to prove results like this very cleanly. From a practical perspective, would you always want to convert something to canonical form? Probably not necessarily. There's a cost to adding these additional variables. You might be able to find a method that is tailored to the structure of the constraints you have. For those of you who program, you may have seen that depending on what kind of computations you need to do, you will use different programs. Programming languages are tailored to the types of operations that are done again and again and again. And if you want to do one type, you use this language. If you want to do another type, use this language. If you're lazy, just do whatever you can do. And so similarly, when you're trying to solve problems in the real world, depending on how things are done, you will do things in different ways. So this proves the inequality. Now we want to show inequality implies optimal. So claim if equal, then x is optimal. Okay. Imagine y transpose c equals x, equals y transpose b equals, I think I'm doing cx, c transpose x. But x is not optimal. All right. It's telling us how to proceed. If x is not optimal, then there's got to be something better. Let x hat have lower cost. Then y transpose b, which is c transpose x, is going to be greater than or equal to c transpose x hat. Thus, y and x hat are feasible, but y transpose b is not less than or equal to c transpose x hat contradiction. So we know that no matter what pair of feasible solutions we get, we have to have y transpose b is less than or equal to c transpose x. So now we just use x hat as our new feasible solution. And so since this relation has to hold for all values of pairs of feasible solutions to the dual and canonical problem, and we have a contradiction, this means that there cannot have been an x hat with lower cost. So if we happen to find two feasible solutions, one to the dual, one to the canonical, such that the costs are equal, then we know we have an optimal solution to the original. All right. Any questions? All right, this is a good place to stop. If you haven't picked up the picture, please do so.